lesson is on partial derivatives. From the first part of section 14.3.
I've never seen I'm
sorry. I can find and apply partial derivatives for a function of multiple variables, which we already talked about before we started the recording. So I'm going to just move into the lesson here. We'll keep going. I'm going to pause for a second. What is a partial derivative? So a partial derivative is when you have a function with multiple variables and you want to find a rate of change if you keep a whole bunch of the variables constant and you're just focusing on one thing. So suppose you're a chemist and you're conducting an experiment and you have some catalyst and you're going to change the amount of this one catalyst and you're going to keep everything else constant to see how this one catalyst affects the experiment. So it's similar to finding the rate of change of function with respect to one of the variables, and you just treat all the other variables as constants. So even though you have a function with you can have 20 variables, if you are doing a partial derivative, you're just looking at one of them, and you're treating all the rest as constants, and you're going to hold them constant while you just focus on this one variable. So this process, this is called partial differentiation. The result is the partial derivative of f with respect to whichever independent variable you're focusing on. And so the next thing, I'm going to have you try to guess the first two partial derivatives you'll ever do. And normally I'd have you do this in groups, but we're in rows, so we're just going to do it independently. Are we ready? Okay. All right, so I have a multivariable function here. Look, you're going to love this. You really are going to love this. Okay, so I have a multivariable function. It's in terms of x and y. 3x minus x squared y squared plus 2x cubed. Y, I want you to try to guess the partial derivative with respect to x and the partial derivative with respect to y. So on paper, just take a minute, take a guess. All right, does everyone have their two guesses? Who needs another minute? Okay. All right, Ian, how you doing? Good? Let's see. All right, turn to someone near you, compare your guesses, see if you match. Discuss, see what you think.
I got 3 minus. Alright, so for the x, 3 minus 2x y squared, so that was 2. And then I got 3 minus 2x squared y dx plus 2x to the third power times y dx. I don't know. I don't know.
All right, let's talk about these. So, f sub x, the derivative first, this is called the first partial with respect to x, and you'll hear me shortcut this, and I'll just say partial x. So I'll say partial x for the first partial derivative with respect to x, and I'll say partial y for the first partial derivative with respect to y. So when we do partial x, what that means is x is our variable, and all other variables you just treat as constants. You treat them as constants. So The derivative of 3x is what? 3 with respect to x, right? The derivative of negative x squared y squared is just negative 2x y squared. Because y squared is just like a constant. It's like a coefficient, right? The derivative of 2x cubed y would be 6x squared y. So your derivative, your partial with respect to x, is 3 minus 2xy squared plus 6x squared y. So you treat, yes, Ian?
For like your documentation, you have to say f subscript x like prime.
No, and that's a very good question. We're going to do notation in just a minute. That's like 2 slides away. But there's no prime notation for partial derivatives. So because you can't, it's too complicated with all the stuff. So you'll either write f sub x or with an x, y, and function notation, or if the function's called z, you can write z sub x. Or you can write, like we kind of have like a dy dx kind of a thing. We could put dz dx, except it's not a d. We're going to learn a new symbol today, so to show that it's a partial. Yes, Tejesh?
So how would you like, I guess, write something down if it was like the second partial x? Or...
That tomorrow we're doing second derivatives. Today we're just doing first partials. Tomorrow we're doing second partials. Because you're going to have partial x, partial x, partial x, partial y, partial y, partial x, partial y, partial y. Like you'll have, there's 4 second partials. So we're going to do those tomorrow. Okay. All right. So now that you've got this, does that change what anyone thinks is for partial y, or are you all ready? All right. What's the derivative of 3x with respect to y? What's the derivative of 3x? 0. It's a constant. It's a constant. Goes to 0. All right. What's the derivative of negative x squared y squared? Negative 2x squared y. All right, and then what's the derivative of 2x cubed y? 2x cubed, right? Yes?
So you don't need like dy dx or anything like that?
Nope.
Okay.
Nope. There will be a chain rule that we will learn on Monday. But we don't have to, there's no chains here because all the other variables are literally constant. Yeah.
This is kind of unrelated, but if we had to miss either Tuesday or Wednesday next week, which one would you recommend?
That's a fair question.
Jack and I need to know.
Let me, oh goodness. All right, so, I was lying. It was this slide. Okay, so notation. So, what is that? So, the first time I was trying to learn this was a couple of years ago, when I was trying to learn, or relearn, it'd been 20 years since I'd looked at a partial derivative. So the first time that I was trying to relearn partial derivatives, and I was looking in the book and I was trying to figure it all out, I didn't notice that these were squiggled D's. I thought they were just italicized D's, and I thought they were just doing d dx of f of xy. And I thought this was just a dz dx, and I couldn't figure out how do you know when it's a partial derivative versus a regular derivative. And then all of a sudden, I had to actually dig in on the internet and found that is not an italicized D. It's this squiggle that looks like a D, and it's called a del. So it's not a Greek letter. No, like D-E-L. Yeah. So it's a math symbol, and it really is just basically a squiggle D. So you write them like that now?
Yeah.
Then you'll have to do something to differentiate between a regular D and yeah. Yeah.
I need confirmation.
So anyway, so if we're doing the partial derivative with respect to x, you can write del x of f of xy, or f sub x of xy, or z sub x, or del z del x, partial z partial x. So I tend to just use the subscripts the most often. I think they're the fastest and easiest way to write it. But it's your choice. You are welcome to use any method that you like. Okay, so that's notation for partial derivatives. Use the squiggle D. Yes, Ian?
I understand like the Z being like a placeholder for like the whole FX thing.
Yeah.
Why would it be
Z, because Z is like your Y in 2 dimensions. Z is now like your 3 dimensions. Like if I write f of xy equals 2x plus 3y, that's exactly the same as writing z equals 2x plus 3y, right? So if I want partial z partial x, like if I want z sub x, that's the same as del z del x, right? So partial z partial x. Okay. Yeah, we have to get in the habit of learning that z is like your output whenever you're doing a multivariable function. Good. Any other questions before we move on? Okay. So I want these on your whiteboards. Tomorrow we actually have a really fun whiteboard activity, but today we're just going to do this. So there are 3 problems. So I want the limit, a little practice with limits as x comma y goes to 0, 0. I want the first partials for those 2 functions in number 2. And just for fun, I want you to find all the values of x and y so that both partials equal 0 at the same time if f of xy equals this. Ready, set, go. Work out there. So the first one, I think every single group got D and E. Yes, yes. Okay. So, and I saw a variety of approaches. So this group did, the limit is x comma x goes to 0, 0. So they changed all the y's to x's and then factored out an x top and bottom, which is really nice. And then when you plug in a 0, you get a limit of 2. That works out really well. And then they did 0 comma y goes to 0, 0, which means they plugged in a hard 0 for the x's. So when you plug in a hard 0 for your x's, those are gone, and you just get negative y squared over y, which reduces to negative y over 1, which then when you plug in a 0 for y, you just get 0, right? So as long as you get 2 different limits, let's see, where's my, oh, there we go. Look at that. Oh, I did x0, which is basically I plugged in a hard 0 for my y, and then plugged in a hard 0 for my x. But this is beautiful too, right? They're both fine. So anyway, technically, actually, as soon as you hit 1, that's a true D and E, you can actually stop, because if any of them hit D and E, then it's D and E. But anyway, okay. All right, so well done. I don't know, let's see. You all got D and E. I'm going to assume that you all did it properly and found 2 different roads, right? So, okay. All right, so first partial. So the derivative of cosine is what? Negative sine. So we have negative sine of, do the guts change? Not at the beginning, no. So you have negative sine of x squared plus y squared times the derivative of x squared plus y squared, right? So now this is where the partials come in. So if you're doing, whoa, that's me. Okay. So if you're doing partial x, then you would have negative sine x squared plus y squared times 2x, right? And then that would just, be gone, go to 0. And then if you're doing partial y, you have negative sine of x squared plus y squared times 2y. So flipping them around, good. Yeah, good. Yeah, I think these all look good. Good. Yeah, they're not all real easy to read. Yeah, I think everybody got it. Well done. All right, part B. Oh, isn't this beautiful? What rule does it require? Quotient rule, right? Okay, so if we're doing partial x, what's the derivative of the top? Y squared, right? The x goes to 1, y squared just stays y squared. So it's y squared times the bottom minus the top times the derivative of the bottom, which would just be 2x all over the bottom squared. So you end up with this beautiful thing right here, which simplifies down to this. Now, I know we are very anti-simplifying in this room.
I
My AP Calculus students, the first part of their Chapter 3 test today, we required that every single answer be written as one completely simplified, fully factored, completely reduced single fraction.
Oh, wow.
And that is just killing them. Like it's funny. Like they can all do the most complicated derivatives, but it's the simplifying where like they're all losing points.
We don't
So.
apply it all the time.
Because yeah,
we never applied.
Now
Yeah.
we're even farther gone from it.
right, yep. So maybe what you're saying is I need to force you to simplify.
No.
That is what I hear you saying.
Who said
Okay.
Maybe like future generations.
Maybe.
We
Okay.
already started the course.
We're pretty
Partial y.
We're also perfect human beings.
So again, we'd have to do quotient rule, but the derivative of the top now, instead of being y squared, is going to be 2xy times the bottom minus the top. Now times the derivative of the bottom, which would be 2y over the bottom squared, and then that simplifies to that. And it looks like you all had the right idea. I think I see all good work. Yeah. Oh, wait. Yep, nope, good. That one's good. Just want to make sure you all remember quotient rule. Yeah, good. All right, the last one. Find all of the values such that both partials are equal to 0 at the same time. So first you have to find the first two partials. So your partial x would be 9x squared minus 12y. And you set that equal to 0. And then your partial y would be negative 12x plus 3y squared. And you set that equal to 0. So then how do you solve this beautiful system? It's just substitution, right? So I solved the first one for y, substituted that in for the y in the second equation, and got this lovely thing, did a little factoring, and ended up with 0 and 4 over the cube root of 9. So is that what 1.92 is?
I have no idea.
Let's see.
My bad.
Let's see.
See, like I don't.
4
Yeah, no, that's right.
It is.
divided by
Oh.
9.
Let's go.
There's a no calculator question.
Yes, that's 1.92. Good, you got it. Did you get the 0?
But as for
You got the hard one though.
Yeah.
Okay. So you know what happened? You divided out a variable, right?
Yeah.
So yeah, as soon as you divide a variable from both sides, you lose your 0 solution, right? So never divide out a variable. Just move everything to one side and factor. You guys got the 0, 0, and you got, look at that exact, right? Very nice. Okay, good. I don't know, bro. Are you calling me bro?
Rishi, talk to me, bro. What are you doing? Give him it. My dog.
That's condescending.
Okay. You know what? You have the right setup. You just needed to go further. Okay. You guys have the right theory. Yeah.
Is that question?
So this one. You guys have 0, 0. Something happened. This says cube root of 9. Yes, it is. That's right. Okay. Root of 2/3. Got it. Okay. All right, that works.
It's like inevitable that something.
You guys got your 2 partials, and you solved, and you plugged in. You just didn't finish. So you were on the right track. So that's good.
Got a lot of names.
Okay. All right. There are going to be a lot of systems in this unit, so get used to having to solve systems of equations. So you're going to get a lot of problems throughout the unit with 2 equations in terms of x and y, and you just substitute and solve. So it comes up a lot. Okay. What does a partial derivative, you okay?
That was so cool. Yeah. I balanced the marker all the way to the thing, and then I rolled it.
Good. Okay. All right. So I'm not going to show you the GeoGebra slide. I'm going to show you the video instead. so that you can see. And should I record this video on the recording also or no? Yes? Okay. Here we go. All right. Okay. You're going to love this. It is so current and high tech. Okay.
How big should a ground battery be?
Okay. This is not the video. This is an ad.
I saw a drawing, got excited.
Okay, wait. Let's go back to the beginning here. Okay.
We have the variable x. We have the variable y. And we have z, which is a function of both x and y. Suppose that we pick one value for x, and we keep x at this one value as we change the value for y. Each time we change y by a small amount, z also changes by a small amount. At each point, the change in z divided by the change in y is given by the slope of this line.
So do you guys see what's happening? They're holding x constant, and they're showing you partial z, partial y.
Red indicates a negative slope. Let's now pick a different value for x, and keep x at this new value.
So when you do...
Again, at each point, the change in z divided by the change in y is given by the slope of this line.
For a line tangent that's parallel to y, it's in the direction of y, for a line tangent to the function.
The change in z divided by the change in y is what we refer to as the partial derivative of z with respect to y. Every point on the graph has a value for the partial derivative of z with respect to y. Here, green indicates a positive value, and red indicates a negative value. Every point on the graph also has a value for the partial derivative of z with respect to x. In this case, the value for y is held constant, while the value for x changes. Suppose we represent the slope of this line with an arrow. The length and direction of the arrow indicates if the slope is positive or negative, and by how much.
So the direction of the vector is in the direction of your tangent line, and the magnitude of the vector is the size of the slope.
Every point has an arrow that represents the partial derivative of z with respect to x. Every point also has an arrow that represents the partial derivative of z with respect to y. If we add these two arrows together as vectors, then we'll get a new arrow. Let's call this new arrow the gradient of the function z. This arrow always indicates the direction in which z is increasing by the largest amount. The length of this arrow indicates by how much z is increasing in this direction. Much more information is available in the other videos on this channel. Please subscribe for notifications when new videos are ready.
All right.
The song goes crazy. It's like a wacky and like cartoony and it's like.
So, you liked it?
Yeah, it was Franz Liszt.
Good.
That's Hungarian Rhapsody.
It adds a lot to the video.
It's like,
You know, I know it's not the most thrilling video, but it helps you kind of see that, like, when you're talking about a partial derivative, right? So if we hold y as a constant value, so y is a constant, what you've been finding for your partials are what are called like general partials, meaning you didn't plug any numbers in, right? So you got this general partial derivative, partial z, partial x, and then what that gives you is it gives you the slope anywhere on a line where that's parallel basically to the x-axis. So the slope of the function of the line tangent to the function anywhere in the direction of the x-axis. And then if you do partial z, partial y, you can find the slope of the function at any point parallel to the y-axis. And then if you put them together, you get this magical thing called the gradient. And that gradient actually, no matter what, always points in the direction of steepest ascent or steepest descent on the graph. So we're going to get into that because that is what leads us into yet another really awesome war application. We should go out and be in the Army after this because our next application is going to be heat-seeking missiles, right? So anyway, yeah. No, really it's not. It's just going to be heat-seeking particles on a plate. But okay. So, oh, good. We have lots of time. So this problem, I'm going to read it to you. It's going to bring back good memories. Let's see how we do with this. Okay, so the length L, width W, and height H of a box all change with time. At a certain instant, the dimensions are 10 by 20 by 20. If, at this instant, L and W are increasing at a rate of 2 feet per second, while H is decreasing at a rate of 3 feet per second, find the rates at which each of the following quantities are changing at this instant. So we want the rate of change, we want dv dt, ds dt, and dd dt. What kind of a problem is this?
Related rates.
This is related rates. Woo! Okay, so it's not a hard related rates problem, but I want you to take a minute and see what you can do with this. This is going to lead into a few other types of application problems in this unit. So, equals LWH. So we had to do a three-way product rule. Whenever you have to do a three-way product rule, it's each derivative times the other two variables, right? Plus the next derivative times the other two, plus the last derivative times the other two. So it's just plugging in all those numbers, and you get 600 cubic feet per second. There's a 600. There's a 600. Good. You got a 600? Good. Last 600. Okay, good. For those of you who did this on the board. Surface area. So to find the surface area, you have to do 2LW plus 2LH plus 2WH. So you have more product rule. Lots of fun with product rule. Okay, the nice thing though is you get to use regular D's for this problem, right? So you don't have to do squiggles. All right, and then again, it's just plugging in lots of numbers. I got 100 square feet per second. Did anyone else get 100? 100? I see 100. I see something that is close but not done. Okay. All right. Good. Any questions depends on volume or surface area. Diagonal. Okay, so we had a lot of discussion about how to find a diagonal. When you're doing a diagonal of a box, the diagonal is the distance from one corner to the opposite corner, right? That's the diagonal. How do we find this distance? So to find it manually, if you don't know the formula, right? So first, it's a Pythagorean theorem, right, on this. And you know this, that's your height. But you need to know this length right here. But what is this length? This length you get from this triangle on the bottom, right? So if that's your length, that's your width, and that's your height. So then L squared plus W squared equals this squared. So this is the square root of L squared plus W squared. And then this squared plus H squared equals this squared. So what is this whole thing? This whole thing is actually just the square root of L squared plus W squared plus H squared. Which should have made sense if you had thought about like distance between two, like the length of a vector, right? If you had the length of a vector in 3 dimensions and one like the vector itself would be LWH, and one, like this is at 0 and this is at point LWH, then what's the length? It's square root of L squared plus W squared plus H squared. So anyway, all right, so that being said, now I made my life easier and squared both sides, just to get rid of that root. So 2d dt equals, and then just a 2l dl dt plus 2w dw dt plus 2h dh dt. And you plug in a whole bunch of numbers, and when you are done, you get 0. The diagonal is not changing at this moment. Hey, look! Everyone got a 0. Well done. All right. Good. Anyone else get a 0? I see a 0 down there. Yep. Good job. Good job. All right. Do you guys remember that when your dimension's getting smaller, the rate is negative? Okay. Good. That is it. That endeth the lesson.